condensate within the reservoir. So that means in the reservoir, in this case, if we reach to the 2293 pressure, the condensate will start to accumulate in the reservoir around the fractures and around the horizontal well, and we will see the effect of this accumulation on the production. Similar to the first case, I did the calculation for the 2 nanometer, and I found the condensation, the accumulation of the condensate will not start until reaching the 1693 BSI of the pressure. That means this process will help to retard the condensate accumulation, so we will produce more gas before reaching to this point, because the condensate accumulation will close the channels of the gas, and that will result in reduction in the gas deliverability. The third case is the confined case with 4 nanometer pore size, and it was found this case has different impact on the phase behavior, and this case increases the pressure that the gas will start, the condensate will start to generate. It was found the pressure in this case equal to 2772. That means within the 4 nano, the condensate will start to accumulate earlier in the reservoir, and will not have enough time to produce before reaching to this pressure. Similar to the third case, the fourth case of 5 nano show almost like the same behavior of the gas, because the condensate start to accumulate at pressure value more than 3200, and the maximum production of the liquid was between 1.1 to 1%. The most important thing is not the amount of the produced liquid, it's when the liquid will start to generate. Because the earlier the liquid generation, that means the lower the gas deliverability we will obtain from this reservoir.
You want to clarify that green chart, the green line is the condensate in the reservoir, not at the surface, it's not the production.
Exactly. This one, thanks for that, Dr. Amin, and this curve represents the accumulation of the condensate within the reservoir. It's not the produce of the condensate or the oil on the surface. That means the more of the condensate within the reservoir, like it's the worst scenario. That means we will not produce gas, and the produced gas on the surface will be will have less heavy component. So we prefer to delay the production of the condensate in the reservoir in order to achieve better production. Moving from the phase behavior, the second part of the result represents the gas and condensate production. For the first case, the unconfined case, we have the cumulative gas and cumulative condensate production for 30 years of production. And the second graph shows the daily production of each case. It's really important to see the changes in the beginning time of the production, because in the beginning, the process of condensate accumulation will start to appear. So I will focus on the first year of production, and in this graph you can see the unconfined case was able to sustain the production of 4 million for the first 4 months, whereas it was not able to sustain the production to the second 4 months. And the drop of the 2 million happened after almost 6 months. Besides that, you can see the production of the liquid or the condensate on the surface start to drop after 2 months of production. That's because we are reaching to that pressure that will cause the condensate to accumulate in the reservoir. And then we'll compare this case with the other cases to see what is the effect of each confined case and each pore size. The second one is the 2 nanometer pore size. As I mentioned before, the first one is the cumulative production for each case. The second one, the daily production. And if we look at the first years, we can see the 2 nano provide better production for the gas, because the 4 million cubic feet, the 3 million cubic feet, and the 2 million cubic feet were sustained, and the 2 million were sustained longer. Besides that, we cannot see, we can see here the production of the condensate was sustained for longer time, because we are not losing that condensate in the reservoir. The third case is the 4 nanometer, and we can see this case has negative impact on the production. You can see the production here is lower. Besides that, if we look at the early production of the reservoir, we will see the daily production of the gas drop in the first 4 months, and it was not able to sustain in the second 4 months. And even the oil production dropped from the beginning, earlier than the unconfined case and the 2 nanometer case. And all of this changes, it's because of the change in the phase behavior and changing the pressure that will generate the condensate. Similar to the previous case, the 5 nanometer case provide the same trend of production. It's lower the production of the condensate, and it causes the cumulative gas production to drop, and the gas rate was not able to sustain, and the production of the condensate was not able to sustain either. In this graph, I want to mention the summary of all of these cases. So here in this graph, you can see the blue curve represents the cumulative oil production for the unconfined case. The production in this case, after 30 years, was around 8,000, and you can see here the production of the cumulative is not that high because the sample of the gas that we use is not really saturated. It's like lean gas. But we still obtain like we can see from the result, the effect of the 2 nano provide better condensate production, and it was around 12,000, whereas the 4 nano and 5 nano caused the gas condensate production to drop significantly. And you might think this thing is not reasonable because this one has lower size, but because of the change, it's result this condensate to increase. And this table shows the results in details, and we can see here the best cumulative oil production was obtained from the 2 nanometer per size. Similar to the previous slides, in this slide I have the summary of the gas production. In this case, you can see the 2 nanopore provide the best production in the early time of the reservoir. If we like even though it has lowest production in the end, but it provide the best production in the beginning, and here we can look closer at it to see what is the best production for each case. The early production is really important for the producers because most of them, they want to obtain the economic advantages in the beginning because they are not interested to obtain the price of the cost or to obtain the economic advantages after 30 years. So this one provides the best production in the beginning, and this one provides the best production after 30 years. The reason of these changes in the production, this case, like the reason that make the production to go down, because this case has lower value of initial gas in place, whereas the other two cases have higher value of initial gas in place. But in this case, we don't have condensate to block the gas flow, so we are obtaining the best production of the gas in the beginning. In this slide, I will talk about gas recovery factor. In order to estimate the gas recovery factor, we have to estimate the initial gas in place. You can see here the 2 nanometer, it has the lowest value of initial gas in place, whereas the 5 nanometer has the highest initial gas in place. Even though the 2 nanometer has the lowest initial gas in place, but we still, if we move to the gas recovery factor, we still, this case, provide the best gas recovery in the beginning of the production. And as I mentioned before, the reason of that, because all the channels for the gas, they still open, they don't have any condensate to prevent the production of the reservoir. And you see finally, like we have almost the same gas recovery factor, but it's not reasonable to wait to 30 years in order to obtain the same gas recovery factor. In this slide shows the reservoir pressure distribution throughout the reservoir. So the first, this picture shows the initial reservoir pressure, and it was around 3,800, whereas these four figures show the reservoir pressure after 30 years of production. In the 2 nano, you can see the reservoir pressure was the lowest because we are producing more, and besides that, all the fractures, all the pores, they were open. Whereas the 5 nanometer case has highest pressure value because of the blockage of the condensate. This figure shows the oil saturation. Similar to the previous one, this one, the initial oil saturation, and it has value of 0. And these four figures show the oil saturation for each case after 30 years of production. If you look at the 2 nanometer pore size, you see the saturation of the oil, it's never changed after 30 years, and this is the main reason why we are producing more condensate and why we are producing more gas. Whereas the oil saturation in the other cases increases to specific values that will result in lowering the production of the gas and the oil. And finally, I'll summarize the conclusions and the recommendation of my research. It was found that poor confinement has significant impact on the critical properties, and it was found that 2 nanometer decrease the value of reduce the value of the dew point pressure, whereas the 4 nanometer and 5 nanometer increase the value of dew point pressure. After investigating the change in the phase behavior, it was found that the 2 nanometer result in more condensate production and more condensate accumulation within the reservoir. The 2 nanometer reduced the condensate accumulation within the reservoir, whereas the 4 and 5 nano increased the condensate accumulation in the reservoir. Besides that, the confinement case of 2 nanometer was found to enhance the condensate production due to the lowering the value of the dew point along with the changing in the phase behavior. Whereas the 4 and 5 nano cases have negative impact on condensate production. Talking about gas production, the 2 nano enhanced the gas production early on due to the slower attainment of the dew point pressure along with the reduction in the liquid accumulation. Also, the 4 and 5 nano pore size cause the long-term cumulative production to increase, and that can explain because of the increase in the initial gas in place and because of relatively higher permeability in these two cases. And also the long-term cumulative gas production in the 2 nanometer pore size is less than the other cases due to the increase in the initial gas in place. And finally, the 2 nanometer pore size was found to increase to provide best initial gas in place recovery compared with the other cases. And this is the references that I use for this presentation. And now I will be happy to take your questions.
Okay, thank you very much. Are there any questions?
What was the impact of confinement on critical pressure and temperature?
For each case of confinement, this has different impact. I use the sink equations to see the impact. So some of them, they are increasing the value, or some of them, they are decreasing the value. So if you can see the figures that I showed in the beginning.
For the critical pressure and temperature.
This case, like the effect of the confinement in the 2 nanometer, the shift in the critical pressure will increase, whereas in the 4 and 5 nano, the shift in the critical pressure will decrease in this case. Whereas the 5, the shift in the critical temperature change with the change in the nanopore size with the different values.
How long have you been working on this project?
I started working on this project since June last year, from June. So it's almost like 10 months.
So did you spend about 30 seconds a day on it?
More than 30 seconds.
So if you were to tell me on a daily basis, how long did you work on it?
Like, it's not easy to tell because some of the weeks I was not working because I was busy with the classes. But in the last semester, I was like almost working every day, sometimes for 10 hours or 8 hours. I even appreciate the time of Dr. Amin and to meet him every day in the break. So it was like, it was not equal, but I can tell like more than 3 or 4 hours a day.
I really think you have done a good job.
Thank you so much.
I really do. Now, no presentation on project is perfect. So if you were to criticize your own work, what is the weakness of this project? Or is it perfect?
No, there is nothing perfect in the real life.
So if this project has a weakness, what is it?
Like, I think it does not have a lot of weakness, but as my friend mentioned before when she presented her work, because we have the same work, we can use probably more pore size to study the effect of them. but we don't have this